Let's talk about equivalent resistance. Before we talk very specifically about equivalent resistance, let's talk a bit more generally about what, in general, an equivalent component would mean. Okay, so what do I mean by that? Let's consider a large circuit which you divided into two parts, right? So one part of the circuit you're calling A, another part of the circuit you're calling B, and the two wires going from part A to part B. So what you want to do is keep this part of the circuit exactly the same and replace B with a single component. Okay, this is a single component. All right, so if I can do that without changing anything in A, that means all the voltages and current remain exactly the same when I replace B with this single component. If that happens, then this component is called an equivalent components of the part B. Equivalent component. So the question arises that when can I actually find such an equivalent component? There is a very simple way of finding out if a given component can replace a whole part of a circuit without changing anything in the remaining part of the circuit. Okay, so what is that? So let's assume that you can actually somehow cut B out of A, out of the entire circuit, right? So you have B like this, right? And then you are applying different voltages and measuring the current, and then you get a relationship between, okay, if you plot V on the x-axis and I on the y-axis, then you get some complicated relationship between, let's say, voltage and current. This is called the IV characteristics of the part B. Now, if you do the same thing for the component which you selected and apply different voltages and measure the current going through it and plot IV characteristics for this component, if these two are exactly the same, then you can replace anywhere you see B in a circuit with two wires coming out of it, you can replace the entire B with that component. Okay, and that's remarkable, right? So as what you're saying is, as long as the current, if you measure V here and current I going here, and you measure V here and current going on here, as long as the relationship between V and I for the part B is the same as the single component, you can replace the entire B with the single component and nothing in A will change. That's called a equivalent component. So in this context, we can talk about equivalent resistance. So let's take a circuit again, and we're dividing the circuit into two parts, A and B, with two wires going between A and B. And let's say the part B has only resistors and nothing else. And these resistors can be connected in an arbitrary way. Then you can replace the entire B with a single resistance called equivalent resistance. Right? So note that now, let's say if there's a voltage V and the measuring current I, then according to Ohm's law, V over I should always be a constant, right? No matter what V is, if you measure the current going through the resistance, then V over I will always be equal to the resistance. Then if you go back to the original circuit, what you're really saying when you say, if you have a circuit, if you have a component which only has resistors, when you say you can replace that with a single resistance, what you're really saying is, if you measure the voltage V and the current going I inside, as long as this part of the circuit has only resistors, this V or I will always be constant, right? And that is a very non-trivial statement we are making here, right? And I'm telling you without proof. Okay, so what I'm telling you without proof is, if you have a big part of a circuit where there are only resistors and the two wires coming out of that, then you can replace the entire part with a single resistor called the equivalent resistance. So let's formalize what we just said here. If there is any part of a circuit which only has resistors, then if you apply a voltage V and measure the current I going in, then the equivalent resistance R equivalent will be defined as V over I. Note that in all the discussions so far, when I say a part B, for example, only has resistors only, right? Now I'm not saying anything about how the resistors are connected. They could be connected in any arbitrary way. This is always valid, the equivalent resistance, right? Now we're going to look at some very specific connections instead of any arbitrary connections. First, let's look at the series connected connection. R1 and R2 are in series if they're connected exclusively at exactly one end. That means they have to share one end and nothing else should be connected here. So let's say there is another resistor here like this, then R1 and R2 will not be in series. They have to be connected one end exclusively like this. Now our task is to find what the equivalent resistance for this would be. If we go back to the definition of equivalent resistance, we said if you have any part of a circuit, then the equivalent resistance would be if you V over I, where V is any voltage you can apply and current I is the current you measure when you apply that voltage V, then Req will be V over I. So let's do the same thing here. I'm going to apply voltage V here and then measure current I going through there. Okay, so now I can use a KVL. So let's say here this forms a loop here. Okay, so I will do a KVL in this loop and write down the KVL equation. Okay, so going up, I have a voltage increase of minus V, plus I have a voltage drop of IR1, plus I have another voltage drop of IR2. This should be equal to 0. Rearranging, I have V is equal to I times R1 plus R2, which implies equivalent resistance would be equal to R1 plus R2. Let's now look at parallel resistors. Two resistors R1 and R2 are parallel if they're connected to each other at both ends, right? So it means they should share both their ends with a common connection. In this case, they are parallel. Our goal again is to find the equivalent resistance. We will follow the same procedure in order to do that. We will apply voltage V, measure a current I going in, and compute V over I. Okay, so let's assume there is a current I1 going through R1. Let's say there's a current I2 going through R2. Okay, let's say the voltage drop here is V. I mean, we know the voltage drop is V. So using Ohm's law, I can say V is equal to I1 times R1, which is also equal to I2 times R2. Now, if I apply a KCL, at that node, I will get I will be equal to I1 plus I2. Now, note that from the top equation, I can write I1 as V over R1 and I2 as V over R2. I'm going to substitute this in the top equation there. Which will give me I is equal to V over R1 plus V over R2. If I factor out V, I get this equation here. Then according to the definition of R equivalent, I just need to calculate V over I, which will be equal to 1 over this whole thing here. And I can simplify further to get R equivalent is equal to R1 R2 divided by R1 plus R2.